lost my clicker somewhere. I'll be traveling back and forth to the computer to try and get this thing going.
Should we sit up there and for you?
No, I'll be all right. So the quiz should be posted. That'll be due Monday. And then I'll also posted a homework assignment. And I think that is due next Thursday. It's not a very tough one. And so after we finish up with this presentation, you should have all the information that you need in order to complete the homework. And that's due before class starts. That's due actually Thursday by 11:30 p.m. But it shouldn't take you very long. And you can just highlight your answers and then try and do the calculation on the document and just submit that electronically. Like, it's not very tough. All right, so pH is going to be important because it kind of dictates our nutrient exchange reactions and also nutrient availability. And so when our soil pH is low, what can we expect our CEC to be? Correct, low. So low pH, low CEC. High pH, we'll have a better CEC. There are different ways to classify pH. And so when we're talking about the thing that's tough about dealing with pH is that anything below 7, many of us know that anything below 7 is considered acidic. Anything above 7 is considered alkaline. But something that we typically tend to say in soils is that it's becoming more acidic or that it's becoming more alkaline, rather than saying, like, the difference between 5.1 and 5.6, they're still both acidic, but we're saying that it's becoming more alkaline. So the conditions may still be acidic, but it's becoming more alkaline or less acidic. It's just kind of some terminology that we use to kind of indicate which direction on the pH scale we are going. Whether we're going towards the more alkaline scale or coming back down towards the more acidic scale. And so for our macronutrients, we can see that somewhere between 6.5 and 7.5 is where most of our nutrient availability is. And then as we get more alkaline, our iron, manganese start to become less available. They're just not there. The soil colloids are taken up by our basic cations. Many of us have seen this pH scale. When I think about something that is basic or alkaline, I'm thinking like bleach. If you've ever had bleach on your fingers, it's kind of slimy, right? It's soapy. Is something else that I think, and one like lemon juice or something, like if you get that on in like a cutter or something, that's going to burn a little bit. I had this, I was working in a lab one day, and I had a beaker of ammonium hydroxide and a beaker of water, and they both looked the same. And I had spilled a drop on the wash cart, whatever, and I didn't know which one it was. And so what I did is I dipped my finger in the little drop and put a piece on my tongue, and if you've ever stuck your tongue on a 9-volt battery, that's what it tasted like. Except only I couldn't pull the battery off. And so I'm sitting there looking with this ammonium hydroxide on my tongue, and I'm just sitting out, I'm like, I'm running around with my tongue sticking out. And I was like, what do I do to stop this? And naturally you think that if you have a base on your tongue, you would look for an acid to neutralize it, or if you had an acid, you would look for a base to neutralize it. And I was like, I don't necessarily know that I want to be putting an acid on my tongue, so I really just stuck my tongue underneath the faucet and let the water kind of neutralize that. But boom, I'll never forget that one. Going back to our basic chemistry, that the pH in pure water is going to be a mixture of hydrogen plus ions and hydroxyls. Hydroxyls being the negative. and that both of these together must add up to equal 10 to the negative 14. So at pH 7, we would have an equal amount of hydroxyls and hydrogen ions. And so the way that they measured this is that there's a hydrogen ion in the solution, and it will actually associate with a water molecule to form the hydronium ion. But this reaction happens so quickly that it's bouncing around back and forth between these two molecules. And so when that happens, we can measure the hydrogen activity based upon how much this is jumping back and forth and moving around. pH is set on a log scale. It is the negative log of the hydrogen concentration. So when you see these brackets, for those of you that have had chemistry, those brackets indicate a concentration. And we see that as our pH is increasing, that our hydrogen concentration is becoming smaller, which would mean that our hydroxyl concentration is becoming greater. So for every 1 pH unit change, we get a 10x change in acidity. And this goes back to that this is a 10th of 1. This is a 100th of 1, a 1000th of 0.1. So each change that we have is on a 10x scale. So a change for 2 to increase the acidity from pH 7, which is neutral, to pH 5, which is acidic, then we would have a 100 times change in the hydrogen concentration. Also, that if we were going from a pH 7 to a pH 9, that would also be a 100 times change. So many of us might be familiar with some of these sources of acidity. Acid rain, precipitation. We have leaching, which is going to remove some of our base cations, and therefore increasing our hydrogen and aluminum concentrations. Nutrient uptake and other transformations can influence, because we are removing some of those basic cations from solution. Our soil organic matter is going to influence that, because from pH dependent charge. We will have some mineral exchange and some hydrolysis reactions, and we'll go over these in just a moment. Soluble salts can influence our acidity. We increase the concentration of one particular nutrient, and that is going to cause an imbalance somewhere else, causing a change in the hydrogen concentration. And then finally, fertilizers, and especially nitrogen and sulfur fertilizers are going to be large sources of soil acidity, because they will, during the transformations that they undergo in the soil, they end up either creating sulfuric acid, they might create nitric acid, but during the nitrification process, we release some hydrogens back into the soil as a result of oxidation. These hydrogen ions are going to come from carbonic acid. Again, I mentioned nitrification and sulfur oxidation, acid rain, and then plant uptake of cations. And I'm just going to kind of briefly go over kind of where we would get these hydrogens from. So for carbonic acid, during respiration, plants give off carbon dioxide during respiration. That combines with water to form this carbonic acid, which immediately or very quickly undergoes a change to kind of balance, turns into bicarbonate, and from that we have one acid that gets dissociated, or one hydrogen that gets dissociated from that carbonic acid. Again, we will have, if you remember from the pH dependent charge that I went over, one of these hydrogens will dissociate into the soil solution to create a equilibrium in there, and that will give us our negative charges. And then again, we will have that go back based upon the pH of that soil. During this process of nitrification, where ammonium is oxidized to nitrate, throughout that whole process, we can have a release of 2 or 4 hydrogen, depending on the ammonium concentration. For each one of those molecules, we will release 2 hydrogens into the soil. Animal manures and sewage sludge will also release some hydrogens. And then finally, many of us are familiar with acid rain from factories or cars, sulfur and sulfur oxides being added into the atmosphere. We're having a problem with this though. Actually, we used to depend on our acid rain for a lot of our sulfur additions, and so now that we don't have those, the Clean Air Act of 1999 kind of minimized or limited the sulfur emissions coming from our coal-fired energy plants, and now we have less sulfur in our acid rain, and so we're having to add more sulfur from our fertilizers. But remember that sulfur oxidation is going to increase soil acidity. Some of these NOx gases. That's odd. We'll have these NOx gases that will also contribute to it. So somehow we have a real big problem with this acid rain that is now falling on our trees and our forests and basically burning off all the leaves. It's changing the pH of our soils, and then our plants can't grow. And then we can also have some of this acid rain that makes it into our waterways and begins to kill our fish. And so not so much that you would need to write this down, but to understand that plants are going to give off some hydrogens in order to take up some cations, so like potassium, for instance. And so there's 2 ways that plants take up nutrients, and during that process they have to release a hydrogen. So here we have a hydrogen in the plant, and when that hydrogen plus ion exits, the electrochemical gradient becomes more negative. And you can think about this just like a bank account, but in reverse. That when this positive leaves, that this would now become negative 121. So when the hydrogen enters into the soil, it might bind with a anion, neutralizing that molecule, and then the plant can then take up chlorine. This hydrogen will then go back out. When we take up cations, the hydrogen is expelled into the soil and then exchanges with a potassium on the soil colloid. That potassium can then move into the cell because the electrochemical gradient is more negative. So this is more with the gradient or against the gradient, positives and negatives, and this is just more that it's neutral and it doesn't have, that's how we get our anions into plants. Our hydrogen is then attached to the soil colloid, and there's potential for another potassium or some other ion to cation to exchange that into the soil solution. we can have aluminum hydrolysis, and hydrolysis just means splitting of water, where aluminum reacts with water to form gibbsite and releases a hydrogen during that process, right there. And then we will continue on to react with water and form that hydrolysis, and so each one of these we release 4 more hydrogens into the soil. There are 3 pools of acidity: active, exchangeable, and residual. And so active acidity is what they measure. This is just the standard pH that they will measure. They add your soil to water, mix it, and then measure the hydrogen activity in the soil. They'll raise that buffer pH. They'll raise the pH to determine the exchangeable acidity. And so when we neutralize the active acidity, the soil colloids will release this exchangeable acidity in order to create an equilibrium right here. Because the soil is always trying to be in equilibrium. And so if we raise the pH too much, the soil colloids will release the aluminum or the hydrogen so that this is balanced here. And then finally we have the residual activity, which is the aluminum that is locked in, or hydrogen that is in the inner layers of our clay colloid or in our humus material. So once the active acidity is neutralized, the soil colloids will release some aluminums and hydrogens in order to balance that out. And when this is depleted, there will be some residual that fills up the exchangeable that will eventually overcome the active acidity. And so this is what our liming materials will neutralize first. But again, because the soil colloids are going to release aluminum and hydrogen back into the soil, we have to continue to lime. Also remember that we are adding fertilizer materials that are also releasing hydrogen. But in a sandy soil, our residual activity may only be about 1,000 times greater than our active acidity. But in clay soils, we might have a 50 or 100 times, 100,000 times the residual activity being greater than the active acidity, because our 2-to-1 clay soils can hold on to more of those aluminum and hydrogens compared to our sandy soils. And so this is why understanding soil texture, what your soil texture is, and they will do this in the lab too. They'll be able to determine what the texture is, and they'll know that it's a clay soil based on some of the results. And they may adjust your liming rate for that. So you might only need 1 ton in a sandy soil, but you might need 4 tons in a clay soil. Buffering capacity is just going to be that resistance to change. And so you can kind of think of buffering capacity in terms of like reinforcements for a military movement of some sort. Once they send in the first wave, they do their thing. Let's say most of them are neutralized. The exchangeable acidity will then resupply the soil with more aluminums and hydrogens. Just in order so that we can keep that buffering, we can keep that soil kind of stable. And so that buffering capacity is going to influence how much lime we need in order to change that pH. And so soils with a low buffering capacity, like a sandy loam, would not require as much lime. From the slide before, that the sandy soil only has about 1,000 times more exchangeable acidity. So the the reinforcements of aluminum and hydrogen are much less than if they were in a clay soil. So in order to improve our pH, we must apply lime, some sort of calcium carbonate material that will undergo this hydrolysis. Here again we have our carbonic acid and our hydroxyl. So this calcium 2 plus will exchange with some hydrogen or aluminum on the soil colloid that ultimately could associate with this hydroxyl and neutralize either a hydrogen or an aluminum. We see where the hydrogen dissociates from this carbonic acid and bonds with and associates with the hydroxyl, forming water. We're left with bicarbonate and a calcium. And then this diagram is showing where we once had hydrogens and aluminums adsorbed to the soil colloids. We added lime, underwent this hydrolysis reaction, and now calcium has displaced those aluminum and hydrogens, and we have formed the aluminum hydroxide, where I mentioned about the mineral hydrolysis, where aluminum binds with that hydroxide or hydroxyl to form gibbsite or some other element, some other primary mineral. So finally the question becomes, how much lime do I really need? And there are a couple of things that we need to understand before we know how much lime we need. And so one component of this RNV is going to be the fineness factor. And you can think about this as surface area. Granular sugar will dissolve much quicker than a sugar cube. And it's the same principle for lime. That if we have a rock source that's not going to dissolve very well. That's going to take a long time to react. The surface area is not very good. But if we had something that was more fine powdered, that would dissolve much easier or react based on the surface area. I'm trying to get this out. I'm spilling it everywhere. So that is going to be reactive. We are able to cover a large area. We do not have to worry about diffusion, and that will react with the aluminum and the iron much better. It will also, well, first off, it'll undergo that calcium hydrolysis better. Again, it's just dissolving. And then finally, our calcium carbonate equivalent is basically just the chemical composition of the liming material. So we would have 3 meshes, well, at least 2. And so the liming material that passes through each one of these meshes is going to determine the effectiveness of it. So that goes back to whether or not that is this big rock, or whether or not it passes through this 60 mesh and is a very fine powder. So whatever does not pass through this 10 mesh sieve needs to go back and be broken down more. That is going to be large rocks. Again, that's not going to react very well. So we'll send that back to the crusher. It may go through some pulverization, but it is not effective. So that is just thrown off the top. That's trash. If it makes it through a 10 mesh sieve, but not a 60 mesh sieve, that stuff is 50% reactive. It has 50% effectiveness. And so we would divide whatever percent falls through by 50, by 0.5, and have 8.5. And everything that falls through after that is 100% effective. So if it does not pass through a 10 mesh sieve, you throw it out. It is trash. It might not get thrown out as far as the material goes, but you can't really count on it to do anything. Next, the medium-sized particles, you can expect 50% reactivity. And then finally, our very fine particles, you can expect 100%. So for example A, 16% doesn't pass through the 10 mesh, not effective. 39% passes through the 10 but not the 60. Half of 39 is?
Study chickens.
What's that?
I study chickens.
19.5 plus 45.
Chickens.
64.5. So our fineness factor, 64.5. And you can fill the rest of these in and can see how I got that. We have 71 plus 9.5 gives us 80.5. All right, next is going to be the chemical composition of our liming material. And so calcium carbonate, I think it just so happened that it has a molecular weight of 100 grams. I don't think that they specifically set out to find a material, but that is the standard. And so it has a calcium carbonate equivalent of 100 because that's our standard. But as we decrease our molecular weight, we see that our calcium carbonate efficiency or equivalent increases. And so the smaller the molecular weight, the lower the molecular weight, the easier the dissolution process happens. And so this calcium does not require as much calcium hydroxide to neutralize the same amount that it would take for calcium carbonate. It's all just based on the chemical composition of that material. So to calculate R and V, simple math, we're going to multiply the fineness factor times our calcium carbonate equivalent. For this example, that CCE is 80%. Multiplying the fineness factor times the R and V. Some basic math that we've been doing. And so now our relative neutralizing value is 70.8%. This is our new analysis. So going back to those calculations that we've been doing in soils, once you have the analysis, it just becomes a simple rate over analysis equation, right? But we had to figure a couple of these things out to find out the purity and the effectiveness of it so that we can get the same amount as if we applied 100% calcium carbonate equivalent that all fell through a 60 mesh sieve. So we'll go back to our equation. 2,000 pounds of calcium carbonate material over 1 acre divided by 0.708 pounds of this material, calcium carbonate. And we find that we need about 3 tons of material, of this co-op material, or the example material, to equal 1 ton of calcium carbonate equivalent. And so the soil test recommendation will come back like this. You will need one ton of calcium carbonate material. So you'll call the co-op up and you'll ask them for some information. They may or may not have it. But just understand that you're probably not going to get very pure lime when you go to do that, application. So some other things to take into consideration, and some of these are done by the lab, some of them are done by you. The change in the pH required, that's done by the lab. They'll determine that. The buffering capacity, it is up to you to determine the fineness factor and the calcium carbonate equivalent. And then just some things to think about when you're applying the lime. So if you have a large change in pH, if you're trying to change your soil from a pH 5 to a pH 7, and it's a clay soil, it might take you 10 tons to do that. But you couldn't apply 10 tons at one time. You would have, you'd have that much lime sitting out there and it would never react and you'd never be able to do anything. So you may have to do this over a period of years in order to get your pH to where you want, because the exchangeable acidity is going to supply the active acidity. And so we have to continue to neutralize that. So it's going to take over time. In some situations like forests and golf courses, you may have to apply more frequently. And we're going to be relying on water to move that lime into the soil profile. So much like when we apply fertilizer, you want to make sure that you're trying to do this and you're expecting some rainfall to happen, or some water to get that into the profile. In some situations, you may not want to increase your pH. This is probably, you'll probably run into this mostly on golf courses. They use gypsum a lot because they don't need to raise the pH, but they do need to get rid of some of this aluminum or maybe even some hydrogens. And so we'll apply calcium sulfate. Not that you really need to know the equation for how that dissociates, but it will form this aluminum sulfate and our gibbsite. Some other ways you can do that is by using organic matter. So the organic matter, with our pH dependent charge, we can get some, we can raise the pH a little bit quickly. We have the change in the hydrogens dissociating, but we can get an exchange with aluminums being adsorbed to the organic matter. And some of those organic materials may contain calcium. Now going back the other way, there are some plants that require more acidic soils. I've got fuzzies all over this thing. That require acidic soils. Azaleas, and so for anyone who might watch golf, the Masters is known for their azaleas, and so they will have to apply like aluminum chloride or aluminum sulfate in order to get those azaleas to bloom very nicely. Blueberries, also maybe tomatoes, will require acidic soils. One way we can do that is we can add these humic or fulvic acids. I was working with a coal mine that was trying to use excess coal as a soil amendment to improve water holding capacity and also nutrient retention. But one drawback of it was that it changed the pH very quickly. It acidified that soil. We can also use elemental sulfur, again, and aluminum. It's probably easier to change your pH. It's probably easier to increase the alkalinity of the soil rather than it is to decrease the alkalinity. Because by the time we have all that calcium carbonate in there, it requires a large amount of some acidifying source to neutralize the calcium carbonate. Remember, because calcium carbonate is what we use to neutralize the acidity. So if we already have that there, trying to get a soil to come down from pH 8 to pH 6, that'd be just almost the same as trying to get it to go from pH 6 to pH 8. Just some things to consider if you ever run into those situations. And so next week we are going to go over some liming calculations, and we'll look at how much lime, where we can calculate actually how much liming material we actually need in order to come up, removing milliequivalents of acid, and then also looking at how much maybe sulfur or aluminum that we might need to apply in order to decrease our soil pH. So that's all I got for now. Have a good weekend. It's Valentine's Day. Take your lady out. Hopefully, ladies, you guys are taking you out. And we'll see y'all next week. Don't forget about the quiz that's due Monday, and then also the homework that is due Thursday. All right? Have a good weekend.